Well, first of all, thank you so much. Good morning to everyone who's participating online and participating on site in Denmark. Let me just introduce myself a little bit. So my name is Gregor Rieher. I'm part of the EnergyInformatics at the Johannes Kepler University, which is located in Linz in Austria. And let me further extend my sincere gratefulness for being able to present here today, to join this webinar online and have a short presentation about a glossary that we made in order for preparation of the task 22 for report A. All right, so just a short agenda for today. Now, first of all, I'm going to let you know some introductory information about the EnergyInformatics at Johannes Kepler University. Afterwards, I will be shortly touching upon the task 22, the overview, and then I'll hop into the draft presentation of the glossary. And that will be finalized by some outlinings of the future work focus within our research institute as part of IEATS task 22. Now, let me just introduce the Johannes Kepler University, or the EnergyInformatics at Johannes Kepler University, for a second. Now, we've been here located at the Johannes Kepler University in Linz for more than 25 years now. We are a legal form having an association, which is why we're not profit-oriented. And with about 50 employees right now, more or less, we're working on around 90 to 100 research projects, and most of them are let's say national projects, but I would say 1/3 of it are international projects, hence 10 Horizon projects and other European projects as well. Now, what is quite interesting is that the department is, let's say, aggregated within 3 different sub-departments, namely the Energy Economics Group, the Energy Law and Energy Technology Group. And why this is quite important and quite interesting as a, let's say, unique selling point for our institute is because we're trying to look at these problems from a very holistic point of view. Therefore, we do have quite broad aspects of different topics that we are working on, namely energy infrastructure, industrial processes, and demand flexibility being of high importance for task 22, but also different areas, let's say energy communities, energy behavior, or market design in general. Now, without further ado, I'd like to briefly touch upon task 22 itself in order to get a better understanding of why we have created this, this glossary draft and why it is quite important to have a very basic understanding of the used terminologies. Now, the IEA Technology Collaboration Program on the Industrial Energy-Related Technologies and Systems was established in 2005, and its main, let's say, focus is the collaboration and knowledge exchange between OECD and non-OECD countries, both participating and non-participating in the IEATS task, or a task in general. Now, with the main focus of the IETS task being on industrial energy efficiency, but also on decarbonization and cross-sectoral technologies. Now, let's focus a bit more on task 22 itself. We have about 6 task member countries, let's call it that way, and the task itself is all about climate adaptation and energy resilience in industry and uncertainty. We have already heard from the introductory words that there is a strong focus on artificial intelligence and, let's say, other factors that are trying to implement or foresee the different aspects of industrial energy technology and also the changes that come along with climate adaptation. Therefore, the aim of the task itself is also the main focus is the facilitation of the climate resilience and energy adaptation in, namely, energy-intensive industries, as stated here. Now, the most important question you might ask yourself, what is a glossary draft and why have we created this, this draft itself? What you can see here is that it's quite the, let's say, the overlying topic of why we have created this glossary draft. Now, I would say for many decades, industrial energy strategy has mainly been dominated by efficiency, which is the energy efficiency paradigm, right? But this paradigm only works well when the conditions are somewhat stable and also predictable. So let's say the energy efficiency measures that have been focused on or even demanded through the ISO 50001 standards, the BAT reference documents, or the Energy Efficiency Directive are currently set in place, but these assumptions that let's say the conditions are stable and predictable are not fully or do not fully hold at this point of view in time. Now, that's why flexibility was more or less the next step, responding to the variability of prices, the demand, or also external grid signals, right? And after this flexibility in energy systems, the adaptation came into place, right? So this is all driven by the climate impacts. Now, resilience, the biggest circle on the right hand side that you can see, is something different. It is not only the next add-on of these slices that you can see here, but it is more like I would call it like a strategic layer that integrates all of these capabilities mentioned before, and also I would say it determines whether industrial systems remain competitive under these changing conditions, outside conditions. Now, this glossary that I will be presenting in the upcoming slides exists because without a shared, I would say, understanding of this shift, we might risk talking past each other while making multi-million or also multi-billion euro investment decisions in the industry. Now, let's make the circle back to those capital-intensive industries. That for these industries, the terminology is far more than just an academic concern, as you might ask or might say yourself. I would say it truly shapes how problems are framed, but also modeled and in some extent also addressed through these investments and also the policy decisions, right? So industrial assets, which are very capex intensive, such as steel furnaces or cement kilns, do have a lifetime of roughly 20 to 40 years and are somewhat deeply embedded into the surrounding energy, but also infrastructure systems. Therefore, any decisions that are made about the design or any retrofits that need to take place are somewhat a lock-in or have a lock-in effect and also creates an exposure to the energy prices, to climate risks, but also to the existing regulatory frameworks for the upcoming decades, as mentioned before. Now, in this regard or in this context, inconsistent or also ambiguous use of terms, for example, such as energy resilience, energy security, flexibility, adaptation, etc., that can have a huge impact on how the terminologies are framed, how decisions are made out in the industry, and how also the comparison between these investments can also be done or not be done if understood incorrectly. Now, let's say flexibility is sometimes treated as synonym for efficiency, despite the fact that flexible operations may even temporarily increase the energy use or also costs in exchange for a reduced risk of exposure. Now, this is let's say a starter of the words that I will be explaining in just a few minutes when we head into the glossary draft itself. Now, with such distinctions that are not being clearly articulated, it can be quite hard, as I mentioned before, to have comparative assessments as they become unreliable, and the resulting analysis, as I would call them, may point to contradiction or also to misleading conclusions. Now, therefore, let's say a harmonized or try to harmonize glossary can provide a shared analytical backbone that aligns both the researchers, but also as it is quite important to have these convolution of researchers and the industry partners as stated in the IEATS tasks itself or themselves. Now, this alignment is particularly important in international collaborations, as mentioned before, in the IEA task, where those insights should be comparable within each other or also across each other. And it's also from an industrial perspective, from, let's say, a C-level perspective, these kind of shared terminologies improve the consistency of, let's say, feasibility studies, reduce the strategic risk, and allow for scenario analysis that can be compared across each other. Now, this is why we have created this terminology or this terminology glossary, I would call it. And this is why I do want to hop into the glossary draft in more detail right on. Now, as mentioned before, I try to, or I want to have a more research appropriate approach, I would call it. And this is why I do want to introduce you to the research question, the underlying research question that we ask ourselves: why do we need to create this glossary? Or this glossary is a result to answer this question, namely being how can climate adaptation and also energy resilience in industry be systematically defined across diverse sectors. And there were some sub-questions or sub-research questions that were answered as part of the glossary documentation as well. Namely, which technologies and methodologies can enable these resilient energy systems under uncertainty, but also how have industrial sectors integrated flexibility before, and what sectors, from a more broader perspective, have adapted these changes or these approaches in more detail. Now, let's talk a bit about the methodology that we used in order to create this glossary. Again, we used the literature review and also different data sources, namely scientific databases and international reports, to then conduct a search strategy, and then afterwards a screening in order to come up with the synthesis. Now, you might ask yourself what exactly the screening and selection criteria look like. Well, in general speaking, it's only documents within the English language were referenced or used for this, and the oldest source we aim to have the most updated sources in general, with the oldest source being from 2010. But the average publication year throughout all the referenced sources was 2023. And just for your information as well, in total for this glossary, 133 sources were referenced, and even more were looked at or browsed through in order to come up with this glossary. Now, what about the search strategy that we conducted as part of this glossary documentation? We did enter we try to have a very holistic approach to this as well. Therefore, the search query keywords were quite diverse, namely from climate adaptation, energy resilience, namely as part of the name from the IETS tasks, but also coming from industrial energy systems to have this more industrially centered point of view, going to the different approaches of how industries have adapted these changes, namely industrial decarbonization, energy storage, but also going towards the more or less technical focused area in terms of uncertainty, general risk assessment, load management, and also computational methods as well. Now, coming to the more to the analytical framework, as I would call it, these were the terminological words that we tried to explain or tried to have a uniform explanation, drawing from conclusions or let's say references from the reference list or from the search query keywords that I mentioned earlier. We came up with these words that we tried to identify, tried to explain, and tried to have a uniform terminology for all these words or phrases that are mentioned here. Now, I would say the most important ones in terms of ambiguity are climate adaptation, climate mitigation, but also energy efficiency and also energy resilience, as that they are sometimes even within research publications used interchangeably, even though they shouldn't be interchanged or used interchangeably in general. Now, to get more information on how these let's say, conceptual framework in order to push forward the energy transition or the industrial energy transition, different technologies and methods have been mentioned, and these mentioned ones are just an outline of the ones that are mentioned in the glossary as well. Now, you can see that there is different types of storages, both from the electrical as well as thermal side of view, but it doesn't only touch upon the storages, but it rather moves towards the different approaches and different methods of how these frameworks, of how these changes are implemented, namely digital twins, which we'll hear a presentation about in the aftermath of this presentation, but also different approaches in terms of green hydrogen, heat pumps, and other power-to-X systems. Now, as mentioned before, which industries have adapted these changes or are adapting to different climate adaptation techniques, I would call them. this is why we have created somewhat a cross-sectoral analysis of namely 10 industrial sectors, which are listed on the right-hand side. Of course, it is named in the introduction of this presentation that the main focus was the hard-to-abate industries, but quite surprisingly or not surprisingly, depending on your background, the term itself, hard-to-abate industries, is not uniformly defined. Hence, most of them are from hard-to-abate industries or energy-intensive industries, but not all of them, as again, there is no uniform conceptual framework about this terminology. And what is quite important, and this is also, I would say that the research approach that we try to follow is that within this glossary, and that's why it's also called a glossary draft. I would say the validation is needed in order to have a broader understanding, to have a broader working knowledge of the terms that are shown here and are explained in the glossary document itself. This is why, again, we will also have a session in the afternoon to get into more detail, but we were, in order to get everyone on board and have a more interactive session as well. I do have a Slido coming up in a couple of slides, so prepare yourself to get some input from your side in order to get the most out of this glossary document. Now, what would be a presentation about a glossary if I were not to show you some definitions about different terminologies that we identified to be of the highest importance for this topic that we're discussing about. Now, again, as mentioned earlier, something energy efficiency and also energy flexibility have been used interchangeably, even though they shouldn't be. Now, again, if we talk about energy efficiency or efficiency in general, it's always about the ratio between an output and an input. Here, it can be the useful output, which is a more broader aspect in terms of it can be products, but it can also be intermediate products, namely within these consortium. But again, it's all referenced as a ratio towards the energy input that was needed to create this output. And it can also follow two different aspects in terms of trying to achieve the same or higher industrial output with the same or even lower energy consumption. Now, in comparison to this, the energy flexibility is more about I would say that the capability of adjustment from industrial systems to external signals, let's say external price signals, but also to the energy demand itself and the supply in response to external market or grid signals. And the main and the most important aspect of this is that the overall, let's say the overall boundary condition is that the productive purpose is still maintained. And what is quite interesting is that the time frame within these boundary conditions, when you look at it from a less technological point of view, is quite interesting, as these time frame can be within an hour, within a day, within a week, or within a longer time frame based on the sources that we used for this definition. Now, coming to the terms that are actually or part of the title from the IETS Task 22, climate adaptation and energy resilience. It is, in terms of adaptation, again mentioned as before, the adjustment of industrial systems to current and future climate impacts to reduce the vulnerability and also still or while maintaining the operations. Now, the resilience is more about the ability to withstand and adapt to, and also to recover, which is quite an important and interesting aspect as well, or recover from these disruptions and climate-related stresses, while also, again, this is like the green line throughout all these terminologies, while still maintaining the operational functions. And climate mitigation in reference or in comparison to all the above mentioned terms is more centered across or about the measures in order to prevent and also to reduce the greenhouse gas production or emissions in general, in comparison to all the other terms that are trying to adapt, trying to recover or withstand these outcoming, let's say, results from the exhibition of greenhouse gas emissions. Now, what are the key results? So what are one of the key results that are coming along while conducting this or compiling this glossary draft? As mentioned in one of the first slides, I want to stress this because it truly is important both for the academic side, but also for the industry point of view, is that without a harmonized terminology within industry and the academic world, the investments and also the policies that are being created to support this, let's say, green energy transition are somewhat difficult to understand, compare, prioritize, and also justify. Now, therefore, it is quite important to understand that it's not anymore about the energy efficiency itself, but it's more about the energy resilience that should be taken up within industrial complexes or industries, and also the policies themselves in order to combine this, let's say, industrial robustness and also at the same time rely on or supply the operational adaptability. Now, what is quite standing on the last point here on this slide is that uncertainty should and needs to be treated as a structural feature. Now, what do I personally mean about this? Uncertainty, of course, plays a big role in investment decisions right away, but the best or the most common way I'm seeing from literature sources is that uncertainty is treated as a more or less brainstorming activity of what could go wrong, but this can lead into, let's say, contracting directions if the terminologies are used interchangeably. And this is why it's crucial to have a structure and also a framework of those words that are crucial for these or this industrial energy transition. Now, let's hop onto a more or less a technology portfolio. What you can see here, and in this, we try to somehow merge the solutions, technologies, but also methodologies into 4 different aspects in order to get a better understanding of what, let's say, priorities have been touched upon throughout this glossary draft. Now, on the left-hand side, the computation methods, I'm sure we're going to hear more about this later on today in the afternoon as well, but also in this morning session. We'll not go into more detail about this, but it will also be touching within the glossary about the different abilities from storage systems, from different applications of how, let's say, surplus energy can be used to have a power-to-X technology, but also in order how to, let's say, respond to external demands or demand systems. Now, the glossary does not only depict these areas on what I've been discussing about just right now, but also it includes solutions and implementations in these 10 sectors that have been outlined earlier, namely green hydrogen integration, power-to-X, and carbon capture, utilization, and storage. But we should not forget these, let's say, most pressing opportunities which are more on the larger scale and also on the yet to be implemented scale, as I will call them. But it also includes very fundamental steps, namely waste heat recovery, but also the climate risk assessment in general. And again, what it's heading towards, as it was seen throughout these sources that we were screening, is that it's also going towards a very industrially local centered perspective, namely in order to increase the capability of islanded operations and also microgrids. Of course, there is no uniform technology and no uniform solution that is suitable for all the different industries. This is nothing new, but just an important aspect here as well, that the strategies that are named here, but also in the glossary, are very or inherently sector and context specific. Now, before hopping into the Slido questionnaire, I do want to touch upon the exemplary applications that have been outlined in the sources as part of the different sectors that were mentioned, namely for steel, the hydrogen steel making electric arc furnaces, or other opportunities for these sectors. Now, I don't want to go into too much more detail here, as everything is outlined in the glossary as well. I was informed, and thank you, Grace, for this as well, that for all the task members of Task 22, this glossary has been sent out. If someone is interested to read this glossary and also interested to give some feedback on this, I would truly appreciate this as well. You can also contact me. I will have my contact information on the last side of this presentation. Now it's time to get your phones out, or also your tablets, whatever suits best. I do want to get your input on certain aspects as well, and therefore I have created a Slido. You can join by either scanning the QR code, I would truly appreciate it, or you can also hop online, enter slido.com, and then there should be the opportunity or option to enter this, let's say, 246-7-digit code, and then you will be able to see the questions, which I will be pulling up in a second, but I'll just want to give you some time to hop on board. Now, let's move to the next slide. The first question, a very easy one and not very centered around the topic that we're discussing about today, but it's still quite important to see where the biggest majority from the members online, but also on site, are joining us today. And I see there's answers coming in. Thank you very much. So this is a word cloud. We see the bigger the term is written, the higher the number of participants are from this country. So we see a strong focus from Germany and Denmark. And just double check on the online participation. So there's 40 people in the meeting. And I would say as soon as we hit between 60% of it, so 20, 24 people, I will move on. And it's great to see that there is not only within the European Union, but also from people across the world, in order to get a better understanding and to fulfill this, let's say, underlying idea of all these IETS tasks, in order to have a better communication across the world, as I will call it. Now, thank you again. You can always join on the left-hand side if you want to scan your QR code, but I will hop on to the next question right now. Now, very, very interesting question that has come to my mind that was approached from different aspects as well in the literature is, what is the first term that you associate with industrial energy resilience? And please be aware of the word resilience. I truly appreciate it. Is an open word question, so you can enter whatever comes to your mind, and I would truly appreciate it. Now, while people are talking, I also do want to mention what is being, or why this Slido questionnaire was used in the first-hand side. This feedback that you are giving me, and you can give me afterwards as well in a more bilateral communication, is that we want to go over this glossary as well, or one more time, in order to refine it, in order to get your feedback into this glossary, to have a better understanding and a somewhat peer-reviewed document itself that can then be used for further tasks, let's say approaches or work packages in general, to have a better understanding. Now, coming back to the question and seeing your responses, thank you very much again. It's very much, industrial energy resilience is all about robustness, as you were mentioning, and also about security, but also uncertainty. And I would say this is very, very interesting as well, as the resilience can and has been uniformly or interchangeably be used with the word robustness from many slides, or from many sources, I'm sorry. So this is a very, very good aspect that you have mentioned. So the understanding is quite good within this consortium. I truly appreciate it. And we see that some smaller areas of diversification, reliable or battery electricity storage systems, and dynamic responses are, I would say, tools or methodologies of how this can be implemented, how energy resilience can be implemented. Now, let's hop on to the next question. You can choose between these answers. Which uncertainty dimension currently has the greatest impact on industrial investment decisions? So from, let's see, the academic point of view, but also from the industry representatives, if we've got people here joining from industrial areas, I truly appreciate your feedback on this. Is it more about the market uncertainty, the regulatory uncertainty, the operational uncertainty, the technological uncertainty, or the energy security uncertainty. I know it's quite a lot to read, but I try to put in brackets the terms that are coming along with this uncertainty as well, to have a better understanding of where these uncertainty areas are connected to within industrial appliances. Now we can see that the energy security uncertainty is of a big aspect. I do understand, and I do see from the latest resources or references that due to the geopolitical situation, but not only through this, but to the availability and reliability of RES implementation systems into the grid, it is quite a pressing feature. Closely along is the regulatory uncertainty within these changing world, as I would call it, in this very hard to foreseeable changes that are coming up. It is quite hard and quite difficult to have a regulatory certainty, and therefore what is quite interesting as well in this regard is that the regulatory measures are, let's say, from the industry perspective, are referenced or are felt to be always late, right? So the changes are occurring, but the changes in the regulatory aspects are happening too late, or also only implement changes that should have taken place years ago. Now, thanks again for your input. And the last one is the question of how relevant are resilience-related considerations for the current industrial investment and infrastructure decisions. Now, I do want to give you a heads up. Rating it 1 is not at all considered, and number 4 is of critical importance. Number 2 and 3 is something in between, but I see everything's taking place. So thank you again for this. All right, let's see. It is of critical importance, and also one less than of critical importance. And this is actually what we've seen in the literature review as well. It is stated that it is probably one of the utmost importance to have resilience-related considerations. Yet within the implementations, when it truly comes to the investment decisions, it is more or less focused about the resilience-related considerations, as energy efficiency or the security of supply is of somewhat more importance than energy resilience. Now, let's hop on to the key takeaways that I've prepared. Again, there is no universal way. There is no shared terminology, which is why the glossary is of the utmost importance, to have a shared vision, a shared streamlined vision of how we try to approach this. There are certain integrated strategies, and this also goes along with, I would say, more inter-industrial, but also an intra-industrial integration, to have a look at your own industry, but also try to broaden your point of view and look across the boundary limits of your industry in order to get the best out of it, to have reliable and possible early investment decisions in the making. Now, again, it is all about the long-term investment decisions that need to take place right away. And for this, we need to have a joint understanding, and also those digital tools that we'll be hearing out later on throughout this day are needed and are also referenced very often in order to have the best cost and efficiency ratio in terms of foresight, and trying to also integrate and incorporate this uncertainty level. And also within this planning tool, or within these planning steps, it is of crucial importance to have these international collaboration platforms, as namely in the IETS tasks, in order to get the hands-on learning from experiences all over the world. Now, I do want to thank you with this in order to show, or in order to show you of how you can approach me in if you have more additional questions, or if you want to receive this glossary task. Now, thanks again for the possibility to speak here. I know it was a somewhat, let's say, dry aspect to discuss about in the morning, but that's why I truly appreciate your participation, and I hope to be making the most out of today's webinar, and I wish you all the best. Thanks again. And if you have any
Hello everyone, my name is Lu. and I'm from SDU Center for Energy Informatics. Today I will present how I develop a digital twin model for energy-intensive industrial processes and data uncertainty using a Foundry case study. First, I will introduce the background and the motivation behind this work. Then I will go through the case and the methods that we use, and then come up with the results we got, and finally we will discuss and conclude this work. The background behind this work is among the global energy consumption, the industry sector accounts for approximately 40%. And the basic metals production is the most energy-intensive subsector, which is responsible for about 25% of the total industrial energy use. So our goal is become clear now. We need to improve the energy efficiency, but we can't reduce the production output. One approach is to analyze isolated stage, but it may ignore the process interactions and which will affect the overall production output. So another approach is to test using the real factory facilities, but it is not realistic for repeated experiments in real manufacturing operations. So and the real-time responses and the process interactions cannot be ignored. So we must to find a better way to analyze comprehensively and avoid the missing dynamic changes, and also can achieve the several tests. But we still facing some challenges. In the production process, each step are highly independent. So even a small delays or changes in one stage may affect the entire system. And the workers' schedules and the equipment availability and also the operating conditions may vary at a different time. And we are also facing the data limitations. Some parameters of the facilities are missing and incompleted, and also the interactions between facilities have limited descriptions. So to address these challenges, a digital twin model is developed to simulate the entire progress and data limitations. So our objective is to develop a digital twin model to move from static and isolated analysis to integrated real-time and data-driven process understanding. And we aim to capture the real-time interactions and the dynamics. And also, we want to assess opportunities to improve energy efficiency without affecting the production output. And also, we want to enable decision support and uncertainty. This is a case that we used for our case, for our work, and this is a production process from a Foundry. First, the scrap metal is transferred from scrap piece to induction furnace for melting, and then the molten metal is passed to the holding furnace, followed by the casting machine to final shaping. And this is a framework how we develop the digital twin model. First step is to understand the real foundry production process. And the next step is to translate from the physical system to digital system. And then we need to model how each components behave over time. And next, we need to capture the interactions between each step. And finally, we need to verify the model under different scenarios. And this is this figure shows the process dependencies in the digital twin. The first line of this figure is the higher level in the system. When an order when the order comes, the enterprise resource planning will receive the order, and it is a system that to decide what to manufacture next. And then it sends the order list to the manufacturing execution system. This is a system that decides how the foundry to manufacture. And in the middle layer are the physical components of the foundry. The first one is the induction furnace, which is used to melt the alloy from the scrap piece to liquid. And then the melting will affect the holding furnace level. And then the molten metal will transfer by a crane using the preheated ladle to the holding furnace. And the holding furnace acts as a buffer that for store the molten metal. And the holding level will affect the casting continuity. And then there will be another kind of crane that will transfer the molten metal from holding furnace to the final casting machine. And the crane availability will affect the transfer delay. And as a last step, the casting demand will trigger upstream melting decisions. So the energy efficiency depends on not only individual furnace performance, but also on the entire progress. The digital model was developed in Logic, and this is an overview of the status of all equipment in the model. And here we can see we have 6 induction furnace and 3 holding furnace and 5 casting machine line. And there are 3 cancel indicate light. They are green and orange and red. When the green light on, it means that this equipment is free and it is not have been assigned to any order. And when the orange light on, it means this equipment is already assigned to an order and can be assigned to another order, but it's still under waiting for next operation. And if the red light on, it means that this equipment is under operation. Of course, to develop a digital twin model, the data and the parameter are essential. And we have got some data that are provided by company, so they are highly reliable. But some data we just come from the assumption. So this data need to be further verified. And this flow chart, how the order executed. First, when we receive an order, we will check if a casting machine is available. If not, we will check again later. And if yes, we will next choose a holding furnace that will match the order type. And again, if we didn't find any, we will wait to check again later. And if yes, we will go to next step to calculate the metal demand for this order. And then we will check the remaining molten metal currently in the holding furnace if it is enough for this order. If yes, we will directly assign this holding furnace and also the casting machine before for this order and directly to manufacture this order. And if no, we will further to check the induction furnace. And we will assume that we use 2 induction furnaces at the same time for one order. And if we found 2, then yes, we will continue to assign this order with 2 induction furnace and 1 holding furnace and 1 casting machine. And if no, we will check again later until we find 2 available induction furnace. So after we have already assigned this order to all the available equipment, then we will continue to execute next order. Yeah, and verify the model is also very important. To verify the model, we need to confirm that the molten metal is conserved across melting and holding and also the transfer and also the casting stage. And we also need to ensure that each furnace operates within its defined loading and melting capacity. And also for the holding furnace, the storage of it can be exceed its capacity and also can be negative value. Each cleaner can only perform 1 transfer task at a time. It can't transfer for different tasks, many tasks at the same time. And we also need to confirm that all the resources follow realistic state transitions. It can be at the same time being different stage. And we also need to check each order follows the intended production route from order release to casting completion. And we also need to ensure that all the occupied resource are not assigned to conflicting tasks at the same time. And to verify the model, the scenario demonstration and also the model output are important. Currently, we have developed 2 scenarios. The first one is a first come, first serve, which means that when the order comes earlier, it will be manufactured first. And for the second scenario, we develop a schedule called the early deadline first. It's based on the order's deadline when it needs to be delivered earlier, it will be manufactured first. And we developed these 2 scenarios to test whether the digital twin responds to different production logic. And we will also want to generate interpretable operational and energy-related outputs. So we have got 2 kinds of outputs from the model. The first is the individual equipment level outputs, which are the time series data with 10 seconds resolution. And for example, the weight and the temperature and also the power of the induction furnace. And also we have got the fill level of the holding furnace. And also we can got the cast amount of each casting machine. And another one is the order level outputs. For each order, we can get the start time and the completion time, and also the duration of this order. And we can also know which equipment has assigned to this order. And finally, we can go to the electricity consumption and also the electricity cost based on the hourly electricity price for this order. And we have used 200 order to test our scenarios. And we have got the results as shown in this figure. It shows that the early deadline first scenario has a better performance as it reduced the energy by over 100 megawatts hour and cost by over 100,000 Danish krona. And also this scenario didn't show any delivery delay, so it provides opportunity to improve the energy efficiency in the further work. So our work has developed a process-level digital twin architect tool, and we also have implemented the hybrid modeling approach, and we also have generated model-level outputs. But this work still has some limitations. Because some model parameters are based on the engineering assumptions due to limited access to complete industrial process data. And also some data-driven model components still need stronger physical support to improve interpretability and reliability. And the model, although has been checked through the logic capacity, but the full validation against the continuous real production data is still limited. So in the future, we want to improve the validation with additional production records, like use more historical and operational data to compare simulated behavior with real production performance. And we can also add uncertainty and sensitivity analysis evaluate how assumption-based parameters affect model outputs and identify the most influential variables. And we will also develop energy-aware production planning to extend the digital twin towards decision support for reducing electricity cost and improving energy efficiency. And that's all about my today's presentation. Thank you.
Thank you. I think we still have 4 minutes for questions. Do any of you have any questions? Also on the chat. Maybe I would like to have questions to start with to warm up. Can you show the slides with the limit, this future work? Yes.
Yeah.
And you talking about use more. You are planning to use more historical and operational data to do the comparisons,
yeah,
to do the validation.
Yeah.
But the reality actually is that the component factory will never going to collect the data which is not available based on assumption in your simulation, right?
Yeah.
So in that way, how you can do the comparison, and because they don't have the historical data.
If they don't have, we will go on there to search online and find some literature that may have the same problem, and to search how they solve those problems to get some methods.
I think one of the things actually in our task 22, which is new experience, and also which is the first presentation which George did, he mentioned about, but not so much emphasized, but for this our task will emphasize actually is this uncertainty. Because uncertainty is not the same as the first presentations that usually people talk about uncertainty is talking about use brainstorming to identify uncertainty. That is actually is one thing we experience. People have a little bit kind of like confusion or the blurred definition about risk and uncertainty, right? So that's actually one of our tasks we would like to further investigate uncertainty. And one type of uncertainty actually nowadays is, what data available? And if data is not available, and how we are going to delineate it, and how we can represent the report. So they just want to say, I think it's quite interesting for us to show actually there is quite different kinds of type of uncertainties which need to consider, not only just from the climate, from energy, it's also from what we investigate and what the model we build, and to compare with the reality. Yes. Any more questions about the presentation? Otherwise, thanks very much. Good. So.
Hello everyone, I'm Michael from Institute Center for EnergyInformatics, and currently I work as a postdoc in this center. Today my presentation is about Causal Explainable AI framework for identifying the drivers of industrial energy best practice. And here I will use a case study from the cheese powder production processes. This is a general test presentation, and I will start from the motivation and background, then go to the research gap and objectives. Then I will introduce the case study and data foundations, then the proposed Causal AI framework to solve the research gap and objectives. Finally, I will introduce the results of my data analytics and also discuss the contributions and conclude the work. Now I will start from the motivation and the background. In this year, due to the rising energy costs, the carbon reduction targets and the stricter sustainability objectives of all of the world. So achieving the energy best practices are more important for industries, especially for the energy-intensive sectors. But to achieve the energy best practices, it's important to understand which operational conditions causes the energy efficient or the energy inefficient production of operations, and why this efficient or the inefficient operations happens, and what are the influencing factors of the energy efficiency or the energy best practice operations. Here we choose the cheese powder production as a case study because the food manufacturing is one of the very typical energy-intensive sectors. And in the food manufacturing, especially the processes about the heating, cooling, or the drying processes, that consumes a large number of energy for example, the electricity or the heating energies. And especially in the cheese powder production, the production flows start from the milk preparation, then go to the cheese making and a series of food fining processes, the drying and the cheese powder preparations. And the drying is one of the most important stage and the most energy-intensive process in the cheese powder production. In the drying tower, the system should control the humidity and the pressure to reduce the humidity through the heat airflow, so it consumes a lot of the heating and the electricity to fit in the high temperature air to dry the cheese powders. To analyze the energy best practice in the cheese powder drying tower, there are still some challenges because the drying process is very complex industrial process. In practice, first of all, it is very difficult to define what is energy best practice in the cheese powder production. The energy best practice is not only the energy efficiency, but it is a balance between the energy efficiency and the production quality control. And then next, it is also difficult to explain what causes the energy best practice. we should explain to the industry and the users what is the energy best practice and how they can achieve the energy best practice. And to explain how to achieve the energy best practice, we should conduct some interpretable and explainable data analytics to the end users to support their decision makings and optimize the industrial processes to achieve the best practices. When we do the data analytics in the energy best practice research, we cannot only use the traditional data processing methods. In the traditional data analytics, using the machine learning and some AI algorithms, most research topics focus on the high quality and accurate predictions to predict the energy consumptions and the energy efficiency. But in the scope of the energy best practice and analysis, it is a decision-oriented industrial insight and analysis. The industrial end users are more interested in the how they can take the actions to improve the energy efficiency and still keep the high quality productions. So in this research, we should support their decision makings through the explainable and causally meaningful data analytics to tell the industrial problem owners what are the best practice of operations and how they can work to achieve the energy best practices in their real-world productions. So to assist in the industrial and users to improve their production processes to achieve the energy best practice, this study aims to develop a causal explainable AI framework to identify the drivers of the industrial energy best practice, and here we use the cheese pot drying process as a case study to show how this proposed causal explainable AI framework can achieve this. Here is the case study. All the data in this study are collected from a Danish cheese powder production factory, and we focuses on one drying towers. The data involves the physical sensor time series to detect the industrial processes such as the temperature in different checkpoints, the humidity, the pressures, and some other operations related sensor data. Then the record for the production, such as the start and the end time, the requirements, and the production with the components of the productions are also recorded. Then we also collected the energy usage for the operations, including the electricity consumptions and the powers and the heating energy consumptions. In this research, we do do not analyze the time series, but we focus on the batch level and analysis because all the energy consumptions and the production quality are batch level. So to understand and analyze the energy best practice, we should identify and analyze which batches are the energy efficiency and have the high quality products, and which batches are inefficient and with low production qualities. Before we conduct the analysis, we should transform the time series data into the batch level data sets. In this study, we aggregated the time series variables by computing the statistical summaries of the time series per production batch. After the data cleaning and the feature engineering, there are over 3,000 production batches are identified, and each batch represents one production order with the same quality requirements and the same production components requirements in this study. Therefore, each batch we have over 100 features related to the industrial operations and energy consumptions and the production requirements. Next, I will introduce the proposed Causal AI framework to analyze the energy best practice. It is a hybrid framework which combines many advanced machine learning algorithms and data process techniques, including the machine learning algorithms, causal inference methods, and the symbolic regression to learn the symbolic equations to quantify the relationship between the variables. After we acquire the industrial data, they are firstly transformed the batch level data sets as I described in the data foundations. Then the batch level, based on the batch level data, we define two KPIs to identify the groups of the energy best practice batches. The two KPI involves the energy efficiency and production quality. The energy efficiency we use the indicator energy unit, which measures the energy consumptions per kilograms of the products. And the production quality related KPI is called the quality rate, which measures the percentage of the valid products in each batch. Then the Gaussian mixed model clustering algorithm is employed to cluster the batches based on the two KPIs, and then 5 clusters are identified. For better explainable in the real-world applications, then the clustering results are slightly improved through the linear classification. We learn the linear decision boundaries to classify the batches to improve the clustering results. So that the clustering is more clear for the industrial and the users to understand how batches are classified, and which of them are from the best practice groups. Then, before conducting the causal inference analysis, the data sets are reduced through the shaft to select the important features for the causal inference. Because for the 350 batches, 130 features are too much for the causal inference. Through the shaft-based feature selection, about 50 key features are selected. Then we choose 3 data sets to conduct the causal inference. There are the total the complete data sets with all batches and the batches in cluster 0 and the cluster 1. Because the cluster 0 and the cluster 1, they are all the high energy efficiency and they involve the sufficient numbers of batches for the data processing in this study. Finally, the symbolic regression is before the symbolic regression, we analyze and identify the quadratic graph to uncover the cause and effect relationships between the features, and then we conduct the root cause analysis to identify and uncover the key drivers of the energy efficiency and the production quality in features. Then for this cause-effect relationships between the operational physical sensor data and the efficiency or the production qualities, we conducted the symbolic regression to analyze the symbolic equations to quantify the cause and effect relationships, so that the industrial and users can understand how strong the some operational features can affect the energy consumption or the production qualities. Next, I will show you some key results in the complex 5-stage methodological framework. First, I will show you the clustering results on the over 350 batches. The figures in the left is the original clustering result from the Gaussian mixed model clustering, and we can see that cluster 4 only have 3 data points, and this group is far away from any of the other 4 groups, so they are defined as outliers. And then the cluster 0 to 3 are described based on their energy efficiency and their production quality KPIs. Next, the linear boundaries among the clusters 0 and 3 are learned through the logistic regression algorithms to modify the clustering results. So that all the data points in one group are centralized into one group with the linear boundaries. Next, I will show you the results of the causal inference. In this stage, we take 3 data sets. Here is the causality structures for data set 1, which represents the total fat axis, and the structure with the features with the red circles are the relationships between the operating devices and the energy consumption related features, and the blue circles shows the relationships between the devices and the product quality related features. And the right part is the scanner diagram to show the production working flow in the real world. And here we marked the devices in the diagram so the industrial and user can understand the causality results in their own scatter diagrams. Here are the structure for the data set 2 and 3, and here is an example for the root cause analysis. Here for the selected key variables regarding the product properties such as the temperature here and the power usage in the data set. A series causes for these variables are identified in the causality structures. Then the one root cause analysis algorithms is run here to identify some important and key drivers among these features that influencing the electricity consumption and the temperatures inside the drying towers. Next, for the 5 selected features for the energy consumption, and this is 1, 2, 3, and the production quality, this is 4 and 5. We use symbolic regression to learn the equations that can show the causality strength between the energy and quality KPIs and the operational features. Yes, here are the prediction results of the symbolic regressions. And then I conclude the results and explain them based on the real definitions of different devices. Here we can see that especially the sensor here 351, we choose the control of airflow through the suction fan. It is very important to control the energy consumption as well as the production temperatures. And the backfeed pressure is also important for the energy consumptions. And for the production quality, especially the temperatures and other thermal conditions and the heating related temperature sensors are important to control the production temperature within the drying towers. Based on the data analysis from the causal inference, we can make some practical recommendations. The industrial end users can use the energy best practice group identified through the cluster algorithm as a benchmark to improve the operations, and the root causes and the key influence factors identified through the causal influence can be the important indicators that should take care to optimize and improve their processes to achieve the energy best practice. Yes. Finally, I will conclude the study and this project. In this study, we proposed an integrated and hybrid AI-driven data processing framework which combines explainable AI and the causality analysis to identify the energy best practices and explain the causes of the energy best practice operations. The energy best practice in this study focuses on both the energy efficiency and the production qualities. And based on our research, the industrial and users can learn from the causes of the energy best practice to make the decisions to optimize and their operations to achieve the energy best practice in the future work. In the future, this framework can be validated by communicating with the industrial and users to see if the identified causes and identified energy best practice, if they are useful in their real world operations, and we can develop more automatic and the real-time monitoring tools in the industry to help them to achieve the energy best practice in the future. Yes, this is my presentation today. Thank you.
Thank you.
Hello everyone. Thank you for having me, for the invitation. My name is Martin Fischer. I work at the Institute of Energy Systems and Thermodynamics at the TU Wien in Vienna. And today I will talk about flexibility and transformation in energy systems. But really, I'm going to talk about the lessons that we had in a research project that is called Industry for Redispatch, which ended last year. So before I dive deep, I have a question for you, people in the room. How many of you got here via bike? Yeah, a few people. With a car? Yes. With public transport? That's me. And via plane? Okay, so I also got here, as I mentioned, from Vienna and arrived yesterday, and I took the plane. Yeah, as I mentioned before, I took the airplane, and maybe some of you took the car also had a similar problem. Is when you go to the security check, then it gets stuck basically in line. And then what I always get nervous and I really don't want to miss my flight. And I always wonder because they know exactly how many people are going to come through the security check. And they know that it's going to be a bottleneck, and they know that there's going to be congestions. They could take some measures to release those congestions. And that's one thing that's happening in public transport. Yeah. So the same thing that I had to endure at the security check also happens in the power grid. So specifically or especially in the transmission system, you also have those kind of congestions. And the measures that the power grid operator or the transmission system operator is taking, those measures are called redispatch. And this is the first, this is the second part of the title is redispatch. And now I'm going to talk why we need industry for redispatch. So first, I wanted to show, this is a stock photo, but this could easily have been taken in the southern eastern part of Austria. It's really flat, we don't have a lot of industry, but they build many wind turbines. And on some days, when it's windy, they even produce a threefold of their consumption. So they have to transmit all the power that is produced in this part of Austria to the central part of Austria or the western part of Austria, where there's a lot of industry. Well, this is really nice, and it shows that the transformation is happening right now. It also shows some issues that I mentioned before that are taking place or happening in the transmission system. So what the grid or transmission system operator does is that he knows in advance that there's going to be, or anticipates that there will be a congestion in some specific line, and then he adjusts or changes the dispatch of the power plants on each side of the line. So one generation goes up and the other goes down, and changes the flow that is going through this transmission system. And this is called redispatch because they change the dispatch of the power plant, and this happens very regularly. So these are the numbers in Austria. They are public at the Austrian power grid. So in 1 year, 2019, it was 309 days. So pretty much this is occurring every day, and it's really expensive. So on average, since 2017, it did cost more than 100 million euros per year. And a lot of it is done via thermal power plants that are carbon intensive. So the other part, as now speaking for Austria, we have a lot of hydro pump storage. So 40% is hydro pump storage, and around 55% is carbon-intensive thermal power plants. So this is kind of the outline of the project. So I already mentioned the part on the right side, where you can see the dispatching or the redispatching of the power plant, shifting the generation up and down. At the same time, we have the rising congestion volumes and costs. This is all happening at the transmission system level, so the highest level of the power grid. And also we have the growing shares of renewables, which are happening on the lower grid levels. So we also have to take into account what is happening on the distribution system on the lower grid levels. And then this happens. So this is the clean energy, or Article 13 of the clean energy package from the European Union, and this is already in 2019, so quite a few years ago. They know, or they know that the redispatch costs are getting more and more because of the renewables, and they wanted to make the process more efficient and change it and open it to all technologies. So first of all, they want to make a like a market-based redispatch, which I don't know how it is in Denmark, but I think in most countries it is in Austria and also in Germany. Like this, that you have bilateral contracts between the transmission system operator and power plant operators. So now they want to open it to all technologies, and of course, industry may save the day and be part of the whole redispatch process, be part of the market. And this really was like the idea of the project itself. How can, first of all, industry take part of the redispatch market? How can they supply, deliver their flexibility? Then how must they cooperate with the system operators, both on the transmission level and at the distribution level? And one other part of the project was how can we define a market for those, for delivering redispatch. So I will only focus on the left part of the industry part. And our part in the project really was to increase automation and optimization of industrial power plants and show if they are, or in what way they can participate in the redispatch market. So one of the things that we did was we developed an energy management system, and we did on-site testing for several days. And you can see that's a lot to take into, but we can focus on just in general. You can see on the right side, you can see the default controller. This is how the plant was operating when we started the project. And on the left side, you can see the EMS, the energy management system, what changed when we implemented our management or our control system. So first of all, the industry partner was from the food processing manufacturing company, and they really worked the way they did their production plan was using like paper sheets. So I don't know if people can see this, but really just sticky notes, writing what kind of products they're going to produce. And they had a very specific way of producing meat. It's called sous vide. And that's specific in that sense that you have to reach a certain temperature, and then you have to keep it at this temperature at one point. So what does this mean? It means that you have a very high peak thermal demand at the beginning, and then it kind of goes very slow. And you can see this happening here on the middle part of both graphs, both plots, that you have these kind of spikes. And then, because that's too much of producing heat at once, they have sensible heat storage, and you can see the temperature of the storage on the top side of the plot. And to fill up the storage system, they had heat pumps operating, and you can see them on the lower part of the plot. So if we now look at the default controller, the way that it worked was it didn't have any information about what's going to happen, because as I said, we only had the sticky notes written what kind of products they're going to produce, and the system doesn't know what's going to happen and when it's going to happen. And if you look at the zigzags on the right top part of the plot, you can see the way that the controller works. That there has one sensor, which is the gray line. If it reaches a certain threshold, then the heat pumps are going up. And if it reaches a certain temperature on the other part, then it shuts down. And this, what happens is that the heat pump is going on and off all the time. But you kind of make sure that you meet the minimum storage, which is the red dotted line, but not always actually. And then what we did during the project is that we digitalized the paper sheets, the sticky notes, and now, and this is really the most important part of the whole process, was now the energy management system knew in advance that there would be a heat load, and it could load up the storage system in advance, which made it more efficient. So we did this test for 14 days, and we improved the energy efficiency by 8%. And we also, as you can also see on these plots, on the lower part of the plots, managed to reduce the switching operations by up to 50%. So that was really just energy efficiency. And then we also did another test. Another part of the project was to do this and deliver redispatch. So we had a whole demonstration. We had 4 different partners doing this, and one of these was in Vienna. You can see the nice picture of the combined heat and power plant. This is my colleague, and this is actually the flexible asset of the power plant that we used for redispatch. And what you can see here is this was the operation of the CHP, and you can see we had a redispatch delivery at this time. And what also is really important in the whole redispatch market, or in the way it works, is that you have to commit to some kind of baseline. So, and this baseline is really important in the hours before and after the redispatch call. So it is important to not go in the opposite direction in these hours, because probably if there's a congestion at this time, there will also probably a near congestion at like the hours before and after. So that's really important that you keep your baseline and not go over this line. And you can see that was, although it was a simple example, we kind of needed some kind of energy management system or some kind of control to stop these zigzag lines. And another thing that we did was we identified the potential flexibility in Austria or in the Austrian industry, and for different sectors and also for different parts. And you can see this is where we have a lot of wind and it's very flat. And this part is where we have like the energy-intensive industry, and this is where we have the steel companies. So again, probably we have a lot of congestions going in this direction. So what have we learned? So, and I think this also goes to show what Gregor mentioned in the first thing is, one thing that's important, that we have the same language. And when we talk with power grid operators and we talk with industry, we often had problems when we talked about, for example, the production planning was different. For us, it always meant something with electricity. For them, it meant, really what kind of meat they are going to produce. So they have very specific domain knowledge. And we did a survey at the beginning. Sorry, it's in German. The project was in Austria, so the survey was in German. But what I wanted to show is that we, at the beginning, had a survey about the knowledge of industrial flexibility. And wenig means little. This means I have no clue, and this means I have some idea. So we can see that the knowledge about flexibility in the industry and how to use it, how to leverage it is very little. Then one thing that was always a topic was that for the industry partners, it was always more important to have a smooth operation. And maybe if you produce cheese powder, then you always want to have a reliable production of a high quality cheese powder. So this is one thing that we ran into quite often, that the importance for the industry was always to deliver their products and not, be part of some energy market. So that was always hard to show them that it's actually, they do save energy and they do save costs, and it does make sense for them to take this also into account. The load prediction or baseline prediction, they were very difficult. So as I said, in one project, then we had the sticky notes as the production plan. Turning this into actually like digital data was a really long way. And the key really to make this possible was automation. So we did also implement, our project partner implemented an automation software. Without this kind of automation, the energy management system had no clue what's happening. So this really was a key. And then using this automation, you do have other benefits as well, not just energy efficiency, but for example, for reporting and other things. So this was the lessons learned from the project. I do have some outlook on what we are currently working on. Also, that we thought about would be interesting for tasks. So we do have or are starting a survey. We do have now we do like kind of interview-based survey and kind of trying to find out really not just from the literature but from the people working in the industry, how flexible are they, how much how price sensitive they are, and what kind of future investments they do, and what kind of future participation in electricity markets they are thinking about. Then the idea really was is to put the results into agents and kind of modeling the behavior of different industry clusters, modeling them as agents, and then using those agents and coupling them with a PyPSA, which is a Python power system analysis, I think, and kind of coupling what would happen if those very flexible industry agents are being released basically on the market, and how it affects the system itself. So I'm talking prices and also the grid system. So that's it. If you have any questions, you can ask now, I think. And also,
Time.
Yeah.
Any question? Okay, then I have two questions.
Yeah.
The first question, actually, I saw you do this kind of 72 hours.
Yeah.
And I assume likely it's because of this day ahead and also this electricity price predictions usually is 72 hours.
Yeah.
Is it?
I mean, this really, the 72 hours was, we needed at least 48 hours because you need the day ahead scheduling and then actually doing the redispatch call. So on the one day you calculate your baseline and you send your baseline to the transmission system operator, and then on the second day you actually get the call, which you don't, like they roll the dice. So it's kind of a simulation of the market. So we needed at least 48 hours, and then we did another day just to make sure it actually works. If something goes wrong on one day, then we have another day.
I think that is actually one of the things our task 22 might going to consider to look into it is regarding this prediction uncertainty, because of it's never be accurate of what we predict for the future, right? And I have another question is you show that you investigate in Austria, you have this flexibility in industry, and you have this map here. And then actually is based on our previously investigations, we look at the whole Denmark, we have many breweries and people love to drink beers, right? And then actually look at the whole breweries if they provide flexibility based on electricity pricing. And then actually, so our conclusion, we didn't do the investigation, but our conclusion is if the industry had start to do the flexibility, basically it's going to cause the electricity price this kind of uncertainty. Have you, in your investigation, considered about if you utilize this accumulated flexibilities based on price signals, so what is going to basically is a risk or uncertainty towards the whole electricity market?
Yeah. I mean, so this this really was just a literature review on like the technical potential of flexibility. And we didn't go really further into what would happen, but I think this is similar to what I want to do here. Is I think kind of what would happen if you couple it to like the real world or kind of the
yeah. We have some work about this whole country levels.
Yeah.
And so maybe we can look into it in South Africa too.
Yeah.
Good. Yes. Thank
Hi everyone, my name is Elias and I'm from Sweden, from KTH in the Department of Environment. I'm here to present our ongoing work on the impact of artificial intelligence on energy-intensive industries, and we will address this from a graph theory perspective. Now, we will start with just kind of displaying how we think about the project. So we split task 22 into 3 different parts. The first one about climate adaptation and energy resilience, second about the energy-intensive industries, and third about the knowledge expansion in AI. So these 3 parts, they play very well together, so kudos to the team for developing it. For example, energy-intensive industries, they are often very resistant to change, as they have very high economical inertia. They're expensive hardware, very large, long return on investment. This plays very well with, for example, climate adaptation, as this requires a system to change, and it's also a time factor. You can't really wait until it's the best time. You need to do it maybe not when it's a good time. Pairing this with AI, where you can often squeeze a few percentage points out of the current existing hardware, so it works well with things that don't move very quick because of its expensive hardware, and because of its large growing research field, it's not stagnant, so future potential is huge. So we designed the project like this. We thought it was a good idea to do at the start here. We'll just look into 2 industries, and we choose cement and strategics, critical industries in Sweden. So cement, like steel, there's only one really productive. There's only one actor that produces cement in Sweden, it's Heidelberg. So it's a very critical industry. We then look through SOTA and pilot projects where AI has been implemented in these industries, and then we will try to assess the resilience impact of it. So that way we get a good idea of how AI can impact these industries. The problem is that resilient impact we realized was not it wasn't clear, like the first presentation about the glossary, it's something that needs to be clear, but it isn't. So actually assessing resilience was hard, and we identified 3 problems. So the first problem is about, as you might have guessed, is the actual speech and terms about this. So in literature, it always came up that there's no universal knowledge method. The terms are different. There's an absence of consensus, and vague definitions are used. Conceptual frameworks that works here might not work there, so terms are differently. And this continues, and it's even been like from 2009, so it's a very long-standing issue. So maybe we need to like do a meta view of this. Maybe we need to change how we see it. Maybe terminology isn't the right thing. So finally, the first problem that we state is it is a fragmented terminology, and it has not been solved yet. So state that. The second problem that we saw. I'll go through these sources. There's a lot of text, but like what I want you to just view is when these sources is supposed to assess the impact of on resilience, but they always do very large abstractions. So significantly enhancing productivity, operational efficiency, and innovation It is very interesting for industry and a company to see this. So they might say, oh, AI is great. But when it actually comes down to the fact of the matter, when a company asks these researchers, well, how do I gain this resilience increase? The connection between a component integration of AI to its strategic resilience level, it's never clear in this. Because if you view it from a large perspective, you get a large macro analysis. So the third thing that we want to say is, this source is as close as we came to finding something that does what we envision. So each of these citations is a specific integration of AI in a company. And then they've tried to categorize them based on terminology now. We see this problem one, but we want to do this, but we want to somehow anchor it in an absolute term. So the second problem is this disconnect between levels. So when you actually integrate AI into a company, how does it affect your resilience? You need to be able to state this mechanistically. The third problem that we saw was that conceptual frameworks are very case by case, meaning that when you try to apply it to maybe a bigger system where the setting is different, they often break down or they cannot expand. So they are set, here is where you can use it, here are where metrics from the conceptual framework work, and when you try to move on to a different field or enlarge it, doesn't really apply. Now, one thing that we found that was interesting was this resilience graph, which is actually quite established. We saw it in many different papers. It is supposed to represent like the system performance on the y-axis. It's supposed to represent any performance of the system. So this could be a product production. Maybe you produce computers and you want to produce 5 a day or something. Then this resilience graph is an analytical reactive analysis, meaning that you can do this after the fact that something has impacted your industry. But it doesn't really produce any predictive power. And again, this changes from user to user, and this user has split this graph into these categories based on, again, terminology, which is fine, but it is normative. So a lot of people say this way about maybe emergency, about avoid resist, so we think that it fits well here in this graph. But this might change when another researcher is trying to use it. So the third problem is basically two parts. The conceptual frameworks are either they're too general or they're too niche. And when you use these, the predictive metrics, they are not transferable across industries or settings where you conceptualize these frameworks. So we need something that is modular, scalable, and metrics which stay relevant as the system changes. Moving on to what we actually think can do this, and that is graph theory. So graph theory is one of the things that we investigated, and it has the best potential, we think. So graph theory, in essence, is very simple. It is based on connections between nodes, and these nodes can represent anything. It is a causal system. So here, this system might represent a social network. The simplest possible is between two people, and it has a mathematical representation as a matrix. This matrix is symmetrical, as the woman knows the guy, and the guy knows the woman. These graphs can be larger and can represent different things, like, for example, ecosystems. This ecosystem is very simple, but here we introduce that it can be directional. So, for example, the trash can doesn't eat the mice or the mouse. The mouse eats trash from the trash can. This results in the matrix being asymmetrical. So you can imagine how large these matrices can be, and you can draw conclusions from it. But just to illustrate what's happening with the matrix. Oh, I pressed it. That's good. Then you can, of course, represent other systems like the power grid. The power grid, now we introduce a property to the graph. We say that the connections have a certain weight. This weight now is represented by its voltage, transferable power, whatever. They can be larger, and they can combine all of these features into what we see here. This is supposed to represent like a material flow in an actual company process. It's an abstract process, but again. Here we can see that it has some inputs, and they have produced some outputs, and they have some things in between that needs to happen. Now, talking about graphs, what we and why we chose this to maybe have as a framework, we like to say that a graph in of itself is not very useful, right? You want to model things with it. And survivability is based on the properties and the structure of the graph. So a threat here could be very simple. It could just be that this crystal input that they need before kilotons off, it can be the supplier doesn't really, or the quality goes down, so they have to recall and so on. So this might change to like 1 kiloton this month. In the graph, it's represented just by the weight changing. Another threat could be to this sub-process, you might just remove the node. So let's say this node is a machine in the process and it requires a spare part, otherwise it breaks. Then you don't have that spare part and you can't get it, so the node now disappears. Threats can also impact edges. This might represent an actual physical truck driving from one place in the company to another. If gas prices rises, as this is a gasoline truck, it might force it to shut down. Now, threats impact survivability, but how you manipulate graph also in terms of protected things, like you might use the kiloton here as an example where 4 kilotons is maybe a surplus. You store some of it, and because this goes down, you have anticipated it. Now you can say that, oh, it's okay to have 1 kiloton as we have a silo with crystals that we can use for a month. This might be that you have 2 machines, 1 backup. It's very simple, but in essence, it also affects the graph. Here you might have anticipated this, like the war in Iran, where your graphical things, and you might say that, oh, we already thought of this. In 2 weeks, we have an electric truck that is in-house, and this is a good investment for us, so we can reconnect this in 2 weeks. So graph representations can be very complex. So this is a very simple graph. In reality, you can have different layers. Now, what we saw with material flow is supposed to represent the middle layer there, but you of course have connections like information needs to flow in the company. You need to control different things. This can also be modeled and connected together. So one might be this. The last layer might be some high temperature processes need burnable fuel or high intensity fuel, I should say, and some other processes might need electricity. So you can have different layers. The actual graphs can be enormous. But just to get an idea of what it is. Now, when we say that we think that this solves the issues, it's because of 3 things each addressing each issue. So the first issue with terminology is that the graph doesn't have terminology. The graph only exists as far as it is manipulated. So a threat manipulates it, but as we say, in a bad way. And a good manipulation could be addressing the threats. So for example, here in this picture, it's like we talked about before, the threat removes the node. This inherently disrupts the graph, your system. Adding 2 nodes increases the survivability of your system. And when we now, instead of saying that this is a flexible system, we see it. Like it's very apparent, right? And this is not just in energy or in material. It is transferable across sectors, and the same understanding is the same in another sector. It doesn't change. The second problem that we address with this is the mechanistic view. And here I do a quick example. So this is an actual AI integration in cement. They produced a model that can predict the strength and other properties of cement based on its ingredients. This increased the speed at which you can create actual viable recipes. In a graph, this is also, you can also portray this as a property change. So let's say the top node is the R&D department in this graph representation. This increases the probability of you acquiring a viable cement recipe from 8% per year to 90% per year. You can represent it how you want. Maybe you say 0.1% per month. It goes up to 0.8 per month. It doesn't really matter. The point is it changes the graph, the structure or the property. And this increases your adaptive capacity. Like when we go back to terminology, we want a company that is able to adapt. Then you need different cement recipes so that if a certain material becomes unavailable, you can use a different recipe. This will change this, and in the graph representation, it is also very tangible. So we use the second problem and we answer it with the cause and effect that graph theory is modeled on. The third problem that we saw was the case-by-case applicability. And here we want to say two things, as we see it as two parts. The first part, let me just go to no so I don't mess this. The first part of graph theory is that it's inherently modular, scalable, and moldable to any process that is causal chains, which is, as far as we know in physics, every single system. That is good. That answers the first part of the problem. The second part is applicability. Now, graph theory in of itself doesn't produce anything, but when molded to a specific system, it can produce any metric that you want, right? So here are just some examples where graph theory is already applied. It's not a theoretical framework, it's a pragmatic framework. So it's already used in digital twinning, it is used in ontology, very important for like AI readable system representations. It is also used for topological metrics, which is one of the fundamental transferable metrics in graph theory. And I'll explain just really quick what that is. So say you have a bottleneck. A bottleneck doesn't really matter if it's in an ecological system or in a power grid system. It's the same problem. So this is a very transferable metric across sectors. And speaking of sectors, it is already applied in different sectors. So it is as applicable as we see that it can be. Now, you might question, yeah, it's just the same thing as I said. But let's move on to how we actually see that why do we use this and not just terminology and so on. And that is because we can finally answer the question mark that we had at the start, where all of these connections between energy-intensive industries and AI and how it actually impacts resilience. Before it was, maybe we can say that it impacts resilience, but we can't really prove why. We can only say that, well, previous studies used the same like batteries and that increased flexibility, but now we can say it from a more anchored perspective in these graph manipulations. So what we want to do now, currently and in the future, we want to connect with industry, and we'll do this through one thing, like we actually ask them to say, these are parts of our industry that we see can have a future where AI is involved. We take those parts and then we read through the literature, we establish this collection of AI implementations, and finally we can use now graph theory in the framework of it instead of current terminology frameworks and conceptual frameworks to actually, in a mechanistic way, see the impact of AI in these industries on a strategic level. And then this question mark finally becomes nothing. It feels tangible. In summary, we identified 3 problems when we tried to assess the impact of AI on these energy-intensive industries. It was fragmented terminology, the fractured perspective between if you do a high-level analysis, then you get high-level results, and if you do a very component-level investigation, then you don't get the strategic impact connection. And lastly, the non-transferable applicability of these conceptual frameworks as they are more case by case. We address this, or try to address it then, by using graph theory to ground or anchor the terminology in actual physical graph manipulations. And we will illustrate it by doing this investigation into how AI into these industries have been applied, and then connect them and the mechanism of them to the graph representation of the system. And we expect this to yield a mechanistic view of how AI shows in energy-intensive industries affect its survivability. And of course, if we encounter that this doesn't work, then at least we have shown that maybe we've tried it, and these are the issues with applying graph theory. Thank you for your attention.
Thank you. So we still have 5 minutes to have a question.
Was I on time?
Yes,
okay.
Perfect. Yes, and just to let you know, he had 120 slides. I was so concerned, but he handled it very well. Any questions? And maybe I can start it. Actually, is I can see lots of things which we have been working on. Maybe the first question is I'd like to ask, because of previously we still working on is ecosystem modeling, relatively similar. But we start with actually is using the social network analysis. It's very similar like graph theory, but it's more like, of course, it calls social network analysis, but actually is focused on the network and the relationships. And so in that way, actually, I'm asking is when you do this graph theory, because I didn't read by myself, and I just have my own experience with social network analysis. Actually, they have very much focus on this so-called strong tie, weak tie, and also like use this visualization about which the point is the size of the point to show how the dominating in this graph of the network. And so, and also how thick the link is shows how the relationship is strong or weak. Then my question is, have you considered about use this kind of what I mentioned in your graph theory?
The what's it called, solo?
Because of the size of the point and also the how wide the tie is.
Yes. Like I couldn't really go into everything, but like what you're stating from my perspective is just, it's another thing that from graph theory you can do this, right? Like a property of a graph, like you say, the size of the node, or
yes,
representation of these nodes and the edges and weights and so on. It's all like in graph theory, so it makes sense. But I don't think I will use that, because we will in this just be trying to categorize it from how you manipulate the graph.
okay.
Does that make sense?
Yes, then actually follow up my next question. And have you considered about use graph theory to visualize the uncertainties or the resilience states and conditions, and
so,
how it's going to look like? And
so it's very interesting because like with this, when you try to represent the thing with a graph, you can be very abstract, which is a good thing. So for example, in a process, you might have a probability layer. Like we know with a probability that this will fail. We know with a probability that we have an uncertainty here. So you can implement it to say that we know that we have a resilient system with the 66% chance, or the risk of failure here is this, but this is the part that we do not know. Like a percentage, you can try to model it that way. So you can implement it as a layer if you like.
it's going to be very interesting to see the future work in task automation. Yes.
So hello everyone, my name is Clay, and I work here at the Center for EnergyInformatics. And today I'm going to talk about assessing the risk of industrial participation in the electricity market. And I will use Foundry as a case study. So first of all, this work has been conducted under this Mission Green Fuels, which is a large project here in Denmark where the focus is on developing the whole supply chain of power to X. So the renewable power production, the energy conversion for the fuels, and then of course the utilization of these fuels. And specifically, we here at the center have been in charge of the work package 6 of the Dinflux project, which is part of this Mission Green Fuels. And this project aims at evaluating Power to X's participation in the electricity market. And we do this by mapping the participation model, and then we assess the business potential and the barriers of participation. And then we look into analyzing the strategies of participation. And today I will mostly talk about this process to market tool that we have been developing, where we screen processes for participation in the markets. So the agenda is a bit of background on the tool, and then this risk tier framework, which is a powerful tool. So first of all, the background is the green transition. So we are replacing our supply chain with green intermittent renewable production and these have less control. And we know that for the electricity system, we need to balance demand and supply all times, meaning that we will need more and more ancillary services to compensate when the solar and wind production is changing its production. So we have some different ancillary services, which I will talk about later. So that's where we have the industry come into place. So as a consumer, they can do some additional revenues by participating in the electricity market, and of course also help the grid by participating, so to balance the grid. And these participation also have some further good things. So the grid operators need less physical reserves, there will be higher liquidity in the markets, the renewable production will have higher operation times, and the governments can see less need for subsidies, for example. And the reason why these industrial consumers can be good for demand response is that they are large consumers, so they can actually affect the grid, they can actually help the grid. They are often planned loads, so they can, they are capable of scheduling their loads, so they can actually plan ahead. And then they often have these ICT equipment, so they are able to control their production kind of automatically. And then they are often also price sensitive, so then if they see an opportunity to make some profit, they will go in that direction. So to the process mining tool. So first of all, I think here in Denmark and most European countries have going from this stage where we liberalize the electricity system. So instead of one company controlling the different needs in the electricity grid, it is split out into several markets, making it a bit confusing for the consumers, for example, if they want to participate. So here in the industrial processes. Furthermore, there is a lot of different requirements for each of these markets. So we have some energy markets, the day-ahead and the intraday, and then we have the ancillary service markets. And then in Denmark, we also have split the country into two parts. And then down here we see the time requirements for participation. So you have to do bidding in some days before operation, and then on operation you also can participate in the intraday, and you also can participate in some of the ancillary service markets. So this just shows that it's quite complex for participating. There is a lot of things to take into account, and there is a lot of both time requirements and also physical requirements. So this is where the process to market tool comes into play to make the analysis of market participation, and it takes these challenges you just mentioned into account. So the electricity market is complex. It's divided into many different sub-markets, and then it's also have these different requirements for each of these markets, and then it's developed for the industry. And this tool is a techno-regulatory feasibility. So it means that it compares the regulatory requirements for the markets with the industrial process capabilities. So the tool has these three parts. So we need the process specification, and these are obtained via this questionnaire where the user of the industrial processes puts in their answers in this questionnaire. Then we need the electricity market data to compare with the requirements from the markets. And then lastly, there will be an analysis of the feasibility of participation. And then the tool outputs this list of feasible markets based on the risk for each market. So this is just an overview of the tool. So we have the questionnaire over here, and we have a list of markets here. The questionnaire is divided into 6 questions, which obtains these requirements. So we have the location, capacity, runtime, duration, utilization, and scheduling. 1 question for each. And then, depending on how you fill in the questionnaire, the list of electricity markets will show the feasible markets that is technically available for participation. So for this one, all the markets are available, but then I changed it to only where the process is located in DK1, and when the running time is a bit higher than we saw on this line. And then the list of markets is a bit, the markets that are not available is crossed out. So the markets in DK2 is not available anymore, and the SCR market is not available due to the ramp time of the process. Yeah, so this is just overall the tool, and then to the risk tier framework of the tool. So this is where we look at the ranking, the feasible markets. So in this list is just these markets are feasible, and then the process will not know where to start. It doesn't know, the process manager or something doesn't know which market it will start with to look into participating in. So that's where we try to do some risk assessment of each market. And here we try to use the definition as risk to be exposure to a market imposed obligation that could create some burdens on the operator. So this is a bit different compared to risk when we talk about bidding and portfolio optimization, where the risk is more into prices and revenues and imbalance outcomes and so on. Maybe I should just go here. So the risk dimensions, there are 4 risk dimensions, and then we score each of those with a number between 0 and 5, and then we aggregate the scoring for all the dimensions into 1, and then the output is based on that scoring, giving low to high risk. So the 4 dimensions is seen here on the left. So we have an equipment and product related risk, where the focus is on the production and the degradation of the machinery. So here the source of burden is often when you have to, if you participate in some market, you have to cycle your process up and down, and this could lead to some degradation. On the market related and contract related risk, we have some focus on then we have some commitments when we tend to participate, and these are seen as when we have a burden, for example, that if we bid, we have some obligations to actually fulfill these requirements. Then the operation-related risk is focusing on the interference with the production. So, for example, if we have some staffing needs in the production line, and we suddenly participate in the market, and we then needs to reschedule the process or something like that, then you affect these physical people that are actually doing something in the production. And lastly, the risk of automatic activation. This is regarding the burden of fast delivery of these ancillary services. So you have to, for example, respond in a certain amount of time, and you need your process to and your whole facility to be able to automatically activate and thereby accommodate these requirements from the grid. And yeah, so to the scoring part, we've chosen to score between 0 and 5, with either no burden at all, and then very high burden, and then in between. And then to the aggregation rule, and then the actual classification of the risks. So we chose to do the maximum obligation principle, so taking all the dimension and then seeing the highest scoring, because if one dimension is really of high burden, then this sets the risk of the whole participation. And then this results in 5 different levels of risk, so low to very high. And then to the case study. So I've tried to take Power Tracks as a case study with participation in the day-ahead market and the MFR market. And so for each dimensions, we show here the ordinal scoring and then a bit of explanation. I will not go over everything, but I will just try to compare a bit. So for the operation-related risk, the day-ahead market is, I've written long planning, it's maybe relatively long planning, but compared to the MFR market, the risk is higher over here because we commit to have these the part of our operation being committed to this market, but as a standby. So if we participate, we have some part of our capacity for production that is reserved for this market, but it's potentially not used, so we can use it in our production operation. Yeah, so overall, with the maximum obligation principle, we say that the day-ahead market has some moderate risk for participation, and going for the MFR market is at high risk. And then for some clarification, so for the risk tier framework, this has of course some limitations, and yeah, it's not intended for using for estimating revenue for participating. It's not forecasting prices. It's not quantifying financial risk, and it doesn't really replace process participation simulations. And it doesn't take into account sequential bidding, so the potential risk of participating in like both of these markets at the same time, that could do some increasing the risk of participation. But the risk tier framework is a pre-model stage screening, so it classifies the feasibility markets by risk, and then it extends just a feasible list with the risk, and then it's a quite general framework, so it can be used in other contexts, so for the market, for other electricity markets locations. And then just to conclude, the industrial in the industry can see some potential revenue for providing flexibility to the grid, and then this process to market tool helps to help the industry to connect with the electricity market to check the feasibility of participating, and then the risk tier framework part is used to try to classify each of the sub-markets into how easy it is or how the risk is of participating, so the industry can like have a list of these markets as potentially, and then this market has the lowest risk, so let's start with participating in this one, and then we can extend further if needed. Yes, so this was it from me.
Good. I think we have still quite a few minutes. Questions? Yes, please.
So thank you for your presentation. I have one question, because do your tool only classifies the risks, but does it also, or do you plan to do so to identify like the potential profit that you get from each market?
Yeah. So this tool is just for screening, and so the idea is that the tool, you screen the markets that are feasible, and then you, not in the tool, but in another way, you simulate, if you then participate in the feasible markets, how does the operation change, and how is your potential profits of this? So I'm working on a simulation where we have, like, for example, Lou has used the EnergyLogic, so kind of the same way, but with the Power-to-X, trying to simulate that if you participate in these two markets, then you will change your production scheduling, but you will potentially receive some extra revenue.
I think before we do the simulation, actually, we partly investigate profit by the way of, first of all, we look at for each of the potential market, who are the participants. The participant list actually release it out. Then actually for industries, actually they can see whether they are the minority group or the majority group. So this is one thing they can also check about the feasibility. Another one actually is since the cellular services market, we talk with our TSO, and they don't want to open so much information data because they want to make the market so attractive, because that should not be attractive. There's a bidding market, because this is trying to make the whole energy system stable. So that is the main purpose. So we cannot get any this kind of like analysis what the profit it is in this case based on the available data, but they do announce about how the bidding, the volume of each the market. So we shows about this the volume, basically the need of that market, and also what the volume of the market, and what's the equivalent of the so-called revenue. I mean this profit for the overall that market. I think we have this yearly or monthly resolution, right, for this profit. So that is actually what we can show through the tool, not the simulation. But for the simulation, of course, we can detail decode for this specific type of industry, what kind of profit and what kind of risk is it going to face to it.
Yeah, so in the tool there's a potential but very simple estimation of revenues, but of course, yeah, a simulation is required to do some precise estimations.
Yes, any more questions? Yes, I think one of the things that I was considering for our future task 22 is maybe we can consider to use our example which we have done in Denmark, and then we can look at with maybe participants like from Austria, from Sweden, maybe we can try to do something similar, and based on our developed this framework. Of course, you know, the different cellular services markets in different countries will be kind of quite different due to this requirements and regulations. But the approach method might be can apply, especially this kind of risk analysis framework. I believe actually no matter which country, actually the risk for the participants, industrial participants actually is quite similar. So that's actually we can discuss it in the future. Okay, so thank you very much for attention, and we appreciate you participating in today's webinar, especially for the online participants. I know it's a very long webinar, and usually we don't expect to, but we are lucky to have all our physical participants. And so please follow us up, and there's a web link, and also there is a QR code, and of course we are going to contact you when all the recorded presentations available online. And we have basically it's 4 upcoming events, and one is in Iceland, and 2 is in Iceland, and 1 is in 2 is in Beijing, and they are very interesting activities, and both of them have a conference and a summer school. And for the conference in Iceland, we already closed down in the review process, but you still have opportunities to participate the conference and also the summer school. Actually, is quite interesting topic, and we have experts from different fields, and we have I think we have SDU involved, and KTH, and also have Lund University, and also University of Iceland will create a very interesting, basically is content, and also which is in China, which is extremely interesting because of, first of all, for the summer school, and we have the expert professors from Denmark and Bo, and also professor from UCAS China, and also professor from Italy, and they are this prestige level going to give a very interesting topic regarding climate and energy and the law regulations and technical aspect, and so that is actually is very comprehensive. And also for the conference, and we are going to have a very discussion-based conference, which is we want to make a more active participation and involvement, and especially just want to say to you, if you're still wondering whether you should go, actually we have a very exciting, 2 exciting site visits. We are going to visit Xiaomi and Huawei EV production factories. So that is actually one of the main visit focus is they are going to demonstrate that there's intelligent productions. So I assume actually you heard about Huawei and the Xiaomi, they produce their EVs. It's pretty fantastic take, and also maybe we'll have opportunity to touch them and to see how they produce it. So if you're still wondering, please consider to join, and also the paper submissions is still open until I think 20th of June. For the online task 22 participants, and please be aware, remember we have an afternoon session, and also we have the separate Teams link. So thank you very much, and both online and the physical participation, and thanks for attending, and see you in person. Bye.